All right, we'll take a look at sampling means. And so, what we should have learned from some of the just classwork examples, some of the activities we did in class, when we take our samples from a normal distribution, the sample means will also be approximately normally distributed. Um, and those x bars should be centered around the true mean with the new standard deviation. Right? Remember, this is called standard error, where we have to divide through by the square root of n. Right? So when we're from a normal distribution, sample means, keep in mind, that's when we stack up x bar on top of x bar on top of x bar, and we make that new dot plot. Those x bars should be normally distributed, right? Normal. And they should start to center around the true mean, and they're going to be spread out according to this standard error, right? The bigger the sample, the smaller the standard deviation, or what we're going to call standard error, right? The big thing we should have realized also, I'll just erase that, um, is that sample size, if it was from a normal distribution, sample size won't matter as long as, again, it's from an SRS. Excuse me, writing the wrong thing. Right? So if it's a normal distribution, sample size doesn't matter, but we still want randomness. Now, if we did something like, here's a data set, and just for the sake of seeing it, if you threw this into a histogram, I think it looks something like this, where all of a sudden this has got a pretty heavy skew to the left. So this is just the sample distribution of the observations. Right? If we plotted these 20 boats, we'd get that in a histogram. So the difference here is if we're doing a sampling distribution, what we would do is each person would go and do a random sample of 8 boats, and then we'd start to plot the X bars, so 15, 16, 17, 18, 19, 20, and 21. So each person would go through and randomly select 8 boats, say you selected here, here, obviously we'd let the calculator do the work for us, 1, 2, 3, 4, 5, 6, 7, and then it picked number 3, and you took that average, and we get an X bar. So we come in here and we plot that X bar. And then somebody else came along and did another one, and they got this one, this one, this one, 4, 5, 6, 7, 8. They did their X bar, boom, they're up here at 19. And if we did X bar after X bar after X bar, maybe somebody got way down here, somebody got way up here. All right. What we should start to notice, though, and this is what we saw in class, is these X bars of the sampling distribution, even though this is skewed, even though the sample distribution, the distribution of our data, right, the distribution of the data is skewed, the sampling distribution of X bars, it should still take on that normal distribution. We saw this in class. So what we're bringing from this, even if we're taking data from a non-normal distribution, from a skewed distribution, from a uniform distribution, anything that's non-normal, um, what we should realize is that the sample means will still be approximately normally distributed. And again, the sample means, so this is the X bars, not the actual data. It's when we take a few observations and we average them and we plot the average. So what's allowing us to still get this normal distribution? This is a big part of statistics, something you should go ahead and file away. That's the central limit theorem is allowing us to do this. It says that if we're doing sampling distributions, right, another way of looking at this, sampling distributions are always normal. Right? When we take a sample and we start plotting these sample statistics, we're there. So regardless, still in these non-normal situations, the X bars should still center around the true mean, and they should still have this for a standard error. So, if we went back and we looked at this, these X bars should have stacked up somewhere between 18 and 18 and a half. And I think in that distribution to the left, the true, the mean of the number of fish caught, I think was 18.4. So one thing to realize, again, um, if you have this non-normal distribution, right, a non-normal distribution, as long as your sample size n is large and you're using an SRS, we're still going to get this sampling distribution to always be normal. Right? That's why we can use normal CDF. So a couple notes to be weary of. Um, one, if I can get that out of our way, the reason we can use a normal distribution is because we're taking a sample, right? We're collecting some data, right? We're taking a sample and then taking average. Or maybe we'd be taking a proportion, something like that, right? If we were just looking for the probability that one boat would create a certain, what's the probability of one of those boats caught 23 fish? Well, we couldn't use normal CDF because it's non-normal. Right? So if it was a single boat, we'd have to use a different type of statistics. But because we're taking a sample of 8 boats, 10 boats, 12 boats, and we're going to use X bars, that's why we're allowed, right? Because we took the sample, right, we can look at the likelihood of getting a certain mean. We can use normal CDF because of the sample. We just need, again, right, so your lower bound and your upper bound. What we have to realize is that we have to use this new standard deviation, which we're calling standard error, as we use normal CDF in these sampling distributions. So as you're doing these problems, pretty much two conditions. Either the sample is from a normal distribution, or my cutoff is usually 30. Sometimes we just want to say that this is sufficiently large. Sometimes the sample will be a little bit smaller. We saw examples in class where a sample size of 10, sample size of 15 still normalized, very non-normal data, right? So either we're from a normal distribution or we have a big N, and then the other big thing, we want to make sure that we're randomly collecting our data. We don't want any bias coming in from our sampling methods. So quick example, according to this article, the mean length of song duration for this population of house finches is 1.5 minutes, standard deviation of 0.9. So that's for all the birds. So we're going to collect 25 of these. We're going to randomly select 25 finches, and we're going to take a look at the average song length. So basically we're looking at how likely is it that the average duration of that set of 25 birds is over 1.7 minutes. So jot down some of the basic information. So the average of the population is 1.5 minutes. The standard deviation for the population is 0.9 minutes. Right? Before we move forward, let's make sure that our conditions are met. One, we do see SRS. That's given. The other that we're looking for is, does it mention a normal distribution? It doesn't, but n equals 25. Not quite to that 30, but we're just going to say that's sufficiently large. Right? 30 would make me feel a lot more comfortable, but 25 is going to be big enough where probably any kind of extreme observations are going to be kind of balanced out. So let's talk about our new distribution. Right? So our X bars should be normally distributed around the true mean with this type of spread. So the mean of my X bars, well, if I took sample after sample, the X bar should stack up around 1.5, and the standard deviation of my X bar should be equal to 0.9 divided by the square root of 25, which is 0.18. Right? So from there, we need to go and write a probability statement. Right? We're going to find the probability that my X bars are greater than 1.7. There's the normal curve. So very quickly, that z-score, so 1.7. The mean, again, was 1.5. If you'll remember, X bars were normally distributed around the true mean of 1.5, and my standard error was 0.18. So, and we wanted to go longer than that. Right? So there's 1.7, which is right here. So we're looking for, what is this area right here? That z-score, will be 0.2 divided by 0.18. 1.11. Right, so we're a little bit more than 1 standard deviation away from the mean. And so we'll go normal CDF. The lower bound is 1.7. Upper bound's infinity. Mean is 1.5. And here's the catch. We're using that standard error right here. All right. So take a quick second into normal CDF. So the lower bound 1.7. Upper bound infinity. We use our new standard deviation. So that probability 0.13. So the final piece of the puzzle here, after we've done all of this stuff, is to answer the question. So the probability that an SRS of 25 finches has an average song length of 1.7 minutes or longer is 0.13. So it probably wouldn't be out of the ordinary if we saw, 13% of our samples are going to find this value.